Okay, good morning everyone. Thank you for coming to class. So before starting, please finish extra credit number 3 at home. We will collect extra credit on Wednesday. One more time, exam is on Tuesday at 7 o'clock. Where is the exam? It is in Scott Lab, in the east side, in the basement, number 4. Don't be late, please. We will start at 7. We will finish at 8:15. One more time, please make sure that you make an appointment. If you do not want to take the exam in this classroom, you want to take the exam in another office, please make sure that you make an appointment with that office as soon as possible. Okay, so what is our goal for today? As you may remember, we have posted one homework about the concept of probabilistic analysis. The due date, I think, is next week. We have good amount of time to work on that homework. Please use the practice problem that we have posted with solution. Those practice problems are very helpful to give you the idea what you should do for homework problems. And for preparing for exam, there are some sources which can be used for preparing yourself for the exam. Slides, homework, and solution of all homework except the last one is on the Carmen, practice problems, and extra credit. If you want to find the solution of extra credit, please go on Carmen, click on assignments, extra credit solutions are there. Grader has finished grading for extra credit number 2. I did not bring your graded extra credit to the class today. We will bring it on Monday. Then when we will collect extra credit 3, we will collect extra credit 3 on Wednesday, then after the exam. Then on Monday, for half of our class, we will teach because the concept of quick sort should be taught. And then for second part of the class, if you have time, we will review. Okay, any questions, any comments, anything? Okay, so today we want to solve one more example about the concept of probabilistic analysis. That's a very interesting question. And on practice problem also we have a similar problem. These are problems which are a little bit harder than something that we did in class. And very good questions to give you the idea what should be done in homework. Then we will start a new concept of the quick sort. Let's see what we have here. You have if n is less than 2, then we will return a1. You have a for loop, as you can see, number of iterations here is n minus 1, asymptotically n. Here in line 9, k is chosen randomly out of n minus 1 number. In line 10, sorry, but we have a typo here. This is function. This is not function. It's the same as function. F2NCC here is sorry. Then here x is updated by adding x by the same function in the smaller inputs, then we will return x. As I explained at the beginning, this problem is a little bit harder than problem that we had before. Why this problem is harder? Because of line 10. What's wrong with line 10? In line 10, when you want to evaluate the running time, because other lines are easy. We had similar problems before in Foundation 1 and in this class. But here the issue is, in line 10, when you want to, as I explained, this is see here is missing. In recursive call, when you want to consider the input of the recursive call, the input of this recursive call is k. In other words, if we want to analyze line by line, here the running time of this for loop is n. Running time of condition if is constant, it can be ignored. And running time on line 10 is t of k. Therefore, you can say that here you have the recurrence is tn equal to tk plus cn. You have something like this. Tn equal to tk plus cn. then the recurrence is Tn equal to Tk plus Cn. Why this is problematic? Because K is chosen randomly out of n numbers, 1, 2, n. And we are choosing here K randomly out of n number. K here is a stochastic. We do not know what value exactly should be considered for K. K can be 1, can be 2, can be 10, can be 100, can be n. It can be anything. The only thing that we can say is that K is chosen randomly out of n number, and probability of everything is the same. Probability of 1 equal to probability of 2, probability of n equal 1 over n. Sorry, if I want to be more precise, this is n minus 1. Because K is chosen randomly out of n minus 1 number. Then here K is chosen randomly out of n minus 1 number, then equal to n minus 1. Okay, so then the recurrence that we have here, you have Tn equal to Tk plus Cn, and I have absolutely no idea what K is. K here is stochastic. K is chosen randomly. Since you are choosing K randomly, then you do not know what value exactly should be considered for K. That's the reason that I'm saying that this problem is a little bit trickier than problems that we had before. What we should do with this problem? So, since I do not know what K is, that's my way to approach to problems like this. I usually try to solve problem easier. Guys, see, this is true in general. Always when there is a problem that we cannot solve that problem, it shows definitely there is something easier that we cannot solve that one. Then we cannot jump. In mathematics, no jump is possible. If there is a problem which is easier and we cannot solve that problem, first you have to solve that problem. Then go to the harder one. Because solving the easier one will give you the idea to solve the harder one. Now here, what is the easier problem? Easier problem here is, what about if we find worst case and best case? In this case, as you can see, we cannot find expected. It seems that we have no idea what K is. Then let's find worst case and best case, which is easier. Why worst case is easier than worst case? Because in worst case, you just need to consider the maximum value for we just need to find the maximum value for K. You are choosing K randomly out of n minus 1, and as all of you know that the maximum value for K is n minus 1. Therefore, if you want to find worst case, you just need to deal with this recurrence. Tn equal to Tn minus 1 plus Cn. Then in order to solve the worst case, the only thing that we need to do is to solve this problem. Tn equal to Tn minus 1 plus Cn. It is an easy recurrence. We had problem like this. You can use substitution, you can use recursion tree, and you can find the theta estimate. If you find theta estimate, please check it. That's easy. We have theta of n squared. The worst case is n squared. I could find worst case very easy. That was easy. So, what about best case? Then best case. What we need to do for best case, for worst case, you consider K maximum. K was n minus 1. For best case, we will consider K minimum. Minimum value for K is 1. And if you plug in K equal 1, then you have Tn equal to T at 1 plus Cn. T at 1 is constant, then it is C plus Cn, and asymptotically this guy is theta of n. Then best case is n. Then worst case here is n squared, best case here is n. Any questions? See, we haven't done anything complicated yet, just worst case, best case. That's it. So I found worst case and I found best case. But what is my goal? My goal is to find expected case. The goal is to find expected running time. Because k is chosen randomly, then expected running time here makes sense. Something that you can say is that expected is something between n and n squared. They can be equal, but something between n and n squared. That's something that we can say about expected. Okay, so let's see what do we have here. See, you have recurrence like this, Tn equal to T of k plus c. And then k is chosen randomly out of these numbers. It seems we can have a kind of spectrum here. Because see what's happening here. When you choose k, which is minimum, you got the best case. When you choose the maximum value for k, you got the worst case. It means the minimum value for k gave me the minimum possible running time. Maximum value for k gave me the maximum possible running time, right? Let's see, minimum value for k gave me the minimum possible running time. Maximum value for k gave me the maximum possible running time. You can see that here you have a spectrum for values for k. You can have a spectrum for values for k between 1 and n minus 1. These are values that k can accept. These are values that k can accept. It seems that here we have kind of increasing trend. Which means at 1, you get the best case. At n minus 1, you got the worst case. Means you have a kind of increasing trend for expected values. It means when k gets bigger, your running time also gets bigger. Because the minimum possible running time occurs at 1, and the maximum possible running time occurs at n minus 1, which is the maximum value for k. Therefore, we have kind of increasing trend on k. It means when k gets bigger, expected value for the running time, expected running time also gets bigger. How it can be used? So, in order to see how we can use this fact, first we will divide this interval into 2 parts. Say this guy is n over 2. Then we can consider this interval into 2 cases. Here you have values for k which are less than n over 2. Here we have values for a which are bigger than n over 2. So, and let's denote x running time, number of iterations. Number of iterations in this problem is not down because this is stochastic, because k is chosen randomly. Therefore, x here is a stochastic value. Since x is a stochastic value, I can find expectation of x. I can find expectation of x. This is my expected running time. Everyone, E of t. We had a formula before that if you want to find expectation of x, you can say that this expectation equal to expectation of x when k is less than, say, or equal n over 2, or means plus expectation of x when k is bigger than n over 2. But you have 2 scenarios: expectation of x when k is less than n over 2, you are in this part of your spectrum, and expectation of x when k is bigger than n over 2, you are in this part of your spectrum. As we explained before, since we have some uncertainty, we do not know if this guy happened or this guy happened, this uncertainty should be added as the probability of k less than or equal n over 2, here probability of k bigger than n. Any questions? We didn't do anything complicated. This is just the formula that we had before, very helpful formula. And when you can divide your cases into 2 cases, 3 cases, doesn't matter. Yes, Leo, please.
So why can't you just simply divide or split the best worst case into
I just consider a portion of this spectrum. It doesn't matter if you want to consider 1 term, 2 terms. Doesn't matter.
Okay.
You just consider a portion. It is that you divide your spectrum into two parts. The lengths of these parts doesn't matter. For simplicity, we consider two lengths which are approximately the same.
So we just have one just be like
One third and two thirds. One is not good. I'm saying that when we want to do, consider a portion. Portion means that you do not want to have just one value. That's the reason that I'm saying that consider portion. Portion means that one third one side, two third another side. One fourth one side, three fourth another side. You have this spectrum, you divide this spectrum into two sub-spectrum. You divide this interval into two sub-intervals. The length of that interval doesn't matter. For simplicity, people consider two intervals with approximately the same lengths. If lengths are not the same, final answer won't be different. The only thing which is important is to understand we divide this interval into two sub-intervals. Here, for simplicity, I am considering sub-intervals with the same lengths.
And the reason you split it is so that you're able to find like the E of that.
Exactly. Any questions? Any comments? Make sense? Any questions? This problem is a little bit tricky, guys. Please don't be shy. You'll find it hard. That's very understandable. Any question? My goal, yes, please.
When you split it, does it have to be n over 2 or can it
N over t, 2 n over t, yes. Because the only thing that you do, you divide this interval into two sub-intervals. The length of those sub-intervals doesn't matter. We consider two sub-intervals with the same lengths just for simplicity. It made the problem, no, I don't know, it made the problem easier. Maybe our calculation gets it maybe a little bit more straightforward. That is just for simplicity. I remember that when I was in high school, our teacher was teaching us, and he wanted to explain that why our mind chooses simplest stuff. If I ask you to give me a number, most of you they say 3, 4, 5. Nobody says that 3,562,000. That's unusual. Our minds usually try to find simplest stuff. Because our mind would understand simplest stuff easier. That's exactly the same thing that we do. That's just for simplicity. That we consider two intervals with the same length. If you get this different intervals, see 1, 10, 9, n over 10, final answer won't be different. Okay, so there are some values that we want to evaluate. I think these blue probabilities are easy. And these blue probabilities are easy. These probabilities 1/2. This probability also is 1/2. That's it. What is not easy? These expected values are not easy because we don't know what they are. You have expected value of x k less than n over 2. Expected value of x k bigger than. You have absolutely no idea what they are. But you have heard this from me before, and you will hear this from me a lot until the end of the semester. In mathematics, in most cases, the most beautiful operation is equality. But unfortunately, in many cases, we have no clue to get equality. After equality, what is the best operation? Inequality. Then always when people cannot find equality, they try to find something which is unequal, bigger than, less than, something like that. Here I do not know this expected value equal to what. Then I will ask myself, is it less than what? I do not know this guy equal to what, I have no idea. But the question is, this guy is less than what? Do we have any idea what this guy is less than what? Fortunately, we do. Because the spectrum that you have here has the increasing trend. What does it mean? It means that when k gets bigger, expectation also gets bigger. Here, all values for k that you consider are less than or equal to n over 2. Therefore, the maximum value for k's which are here is k at n over 2. The maximum value for running time occurs at n over 2 because you have increasing trend. It means when k gets bigger, running time also gets bigger. Then you can say that at n over 2, the maximum value occurs. It means everything that you have here is less than t at n over 2. Then how we can be written? We can say that everything here is less than x expectation of x when k equal n over 2. When k equal. Same story here again. Here you are considering values for k which are bigger than n over 2. Then the maximum value here is k at n minus 1, because see the maximum value that you consider for k is n minus 1. Then here you can say that this guy is less than expected of x at k equal n minus 1. Then see, I could not find any equality. Always when you can, because see, always you ask yourself, this guy equal to what? If we have no answer, then we ask this. If you have no answer for this, then great. There's equality, then inequality, then great. For that, we will lucky. Okay, any questions, any comments? Someone can say, is this guy easier than this? Yes. Why? Because see, you have this recurrence here. This expectation is this recurrence at n over 2. Then the only thing that I need to do is to replace k, this recurrence, with n over 2. Okay, let's do it. Then you have t at n over 2 plus cn times 1/2. And the second one, you just need to replace this k in this recurrence with n minus 1. Then you have t n minus 1 plus cn times 1/2. See, by using just one fact that the spectrum that you have for values for k has the increasing trend, you could write these inequalities. And these inequalities that you have here tell us this expected value is less than this. It's still not easy, but better than this. This one was better, but okay. It's still not easy, but a little bit better. Any questions, any comments? Please ask. This problem is a little bit tricky, then you find it hard and very understandable. So then what I have up to now I have is E of Tn is less than, instead of writing Tn also, let's write E of Tn, because you are not evaluating Tn, you are evaluating the expected value. Instead of this guy also, let's write E of Tn. That's more instead of this also, let's write E of Tn minus 1. But we are evaluating the expectation. If E of Tn is less than, I will distribute 1/2 E of Tn over 2 plus 1/2 Cn. For the second one, I will distribute again 1/2 E of Tn minus 1 plus 1/2 Cn. And if you simplify 1/2 Cn plus 1/2 Cn, 1/2 Cn, then you have 1/2 E of Tn over 2 plus 1/2 E of Tn minus 1 plus 1/2 plus 1/2 is 1. Any questions, any comments? Now, that's what I wish I would show. E of Tn is less than 1/2. Still, it is not very easy recurrence. What is the issue? The issue is that you have two recursive calls with the different inputs. That's the issue. But we may be able to get rid of it. See, you have n minus 1 here. N minus 1 is less than. Then what I can write, I can say that this is less than 1/2 E of Tn plus 1/2 E of Tn over 2 plus 1/2 E of Tn plus. What did I do? I just replaced this guy with Tn. Because n minus 1 is less than n, therefore so this guy is less than tn. And when you replace etn minus 1 by etn, you are making this bigger, therefore that will equal that. Why this is better? Because the question that several of the students asked me that how you came to your mind that we should replace n minus 1 with tn. Because now I can move this guy to another side. And still have the same input. And if you move it to another side, you will have e of tn minus 1 half e of tn less than 1 half e of tn over 2 plus and e of tn minus 1 half e of tn equal to 1 half e of tn. See, now I have just one recursion on one side. You will multiply both sides by 1 half to get rid of this 1 half by 2, then you have e of tn less than e of tn plus e of tn. This is not actually Cn, this is actually 2Cn. You multiply both by 2. But 2Cn is constant, and you can say this is another constant. Say C constant. Doesn't matter. 2 times C and C are the same. Both are constant. Doesn't matter which one is which one. So, any questions, any comments? Hope it was not too much calculations. Any questions? Any comments? It's a little bit strange. We haven't done something like this before. A little bit strange. So something that we did here is kind of interesting approach. As you could see, first we divided our interval into two subintervals. Then by using this trick that etn minus 1, now we replace with e of tn, and then we replace etn minus 1 with e of tn, you reach to something bigger. And moving e of tn another side, we could get rid of one of these recursive calls. And now we have just one recursive call. It is an easy recurrence. By using please check that form, and it goes on this slide. By using substitution or recursion tree, you can see very easily that this recurrence asymptotically same as n. Substitution technique or recursion tree technique. I think recursion tree is better. It was in a slide we use the substitution, but recursion tree is faster. You can see very easily that this recurrence is the same as. Then here what did I show? I showed expected value, expected running time is less than. I also can say that it is bigger than. Why it is bigger than n? It is already written here, right? Expected value always is bigger than the best case. Then expected value is less than n, we could show this. Expected value is bigger than n because n is the best case running time. Then here we can say what? Here we can continue. Expected running time is same as expected running time here is same as best case. Because you could bound it from above and below by n, therefore expected running time is same as. Yes, please.
In the inequality, we need to include the c, like cn is less than.
If we want to, yes. What C is a constant, and when C is constant, you can ignore it. For beauty, most people write C. But if you look at, for example, if you read the CLRS, you can see that on CLRS never C is used. It really depends on your style for beauty. You know, some people write C, some people don't. But it depends on. Yes, please. No. This one You are asking, okay, you are not sure if I understood correctly. You are asking if I technically replace this guy with E of
Like
T
in,
N?
in one of the earlier steps, like in the same step where you replace it with T of n minus 1 with.
Oh, okay, I see. For this one, you are asking that if we could replace this with E of
Yes,
Yes.
yes.
So then mathematically, let's say, look, there are two questions here. Number one, can we replace E of Tn over 2 with E of Tn and write this stuff? Yes. Is it helpful? We should see. When I'm saying that is it helpful, it means that why this guy was helpful? Because I got something as the upper bound, which is same as lower bound. Therefore, this upper bound was helpful. But if you replace, technically, you can replace this guy with E of Tn and move this another side and write exactly the same. Do you know what would be the final inequality? Your final equality will be E of Tn less than E of Tn minus 1 plus Cn. See, when writing. If we follow the technique that you are suggesting, if we will reach to this inequality. E of Tn less than E of Tn minus 1 plus C prime n. Asymptotically, this guy is same as n squared. And look, this upper bound is not there. Because we already know that it is less than n squared. So we already know it is less than n squared. Then mathematically, you can replace E of Tn. It means that you can replace this guy with E of Tn. Yes. And write completely the same procedure. Means keep writing n minus 1. And this guy and move this another side, and eventually you will reach to this. But if you reach to this, because asymptotically this recurrence is same as n squared, what will be your final conclusion? You will conclude this expected value is less than n squared. But this is not something new. We already know that it is less than n squared. Therefore, there are two questions here. Can we replace E of Tn over 2 T of Tn? Yes. But the final results that we will reach is not something new. But when you replace E of Tn minus 1 with E of Tn, the final result that you will reach is something new. You will reach to the fact that this guy is bounded by n. Very good question, Leo. Thank you. That's a very good question. Everybody is following what Leo is asking. He is asking you replace this with E of Tn, and you reach to. What about if you replace this with E of Tn? Mathematically you can. But the final result that you will reach is not something interesting, it's not new. But you will reach to expected value is less than n squared. And it is already known. We know that expected value is less than n squared. That's something that we need to remember. For each function, there are million upper bounds and there are million lower bounds. For example, for this function, n squared is upper bound, n cubed is upper bound, n to the 4 is upper bound, n squared log of n is upper bound, many upper bounds. We are interested in upper bound, which is same as lower bound. Then every upper bound is not interesting. The upper bound, which is similar to the lower bound, is interesting because you want to find the theta's. Any other questions? Yes, please.
Can you re-explain why you're shifting one of the events over to the other side of the interval?
You mean these two?
Yeah.
You are asking that why you need to replace one of them?
Yeah, I guess. Like, why? What are we doing exactly?
Because you see, the issue is this: you have two recursive calls with two different inputs. This recurrence is trade-free. In order to make it smaller, in order to make it simpler, one of these recurrences should be cancelled. That's the reason that we do this, because we want to make it easier. Because see, if you have two recursive calls, one of them input is n over 2, another input is n minus 1, this is very tricky. And we don't like something like this. Then we always try to make it easy, make it simpler. See, I remember that when I was a PhD student, very famous mathematician, I asked him why you did this stuff, and he said because they were easy. Everything that mathematicians do because it's hard easy. We don't like hard stuff. We like easy stuff. A recurrences with two different recursive calls and different inputs are hard. Then we try to cancel one. Then here I want to cancel this one, I want to cancel this. As you explained for us, technically you can replace this and you can replace this. But replacing this guy doesn't give us something interesting. Replacing this guy gives us something. Therefore, we do this. Yes, please.
If we were doing this on an exam, would you have to show our work for the solving for EFT and
Yes, yes, this is something that we need for the exam. But if it is mentioned that, for example, you can assume this guy asymptotically is staying like that. This is something sometimes that we might exam. Sometimes like you can assume blah 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 blah. For this question, something which is more interesting is finding expected case by using the trick that we explained. And those stuff sometimes can be ignored. Usually when we can't ignore it, I will mention it in the exam. So for example, you can assume blah blah blah. You can assume blah blah. In those cases, you can. Yes,
So if we had to, then how would we find the asymptotic behavior of E of T on over 2?
How we can find asymptotic behavior of E of T over 2? Sorry, you mean this way, but
Yeah.
asymptotic behavior of this alone doesn't make sense.
Like plus the 2CN, yeah.
It is that how we can find these. I think that recursion to be or substitution.
So it's not the same, because you're still like plugging it back into the same function that we're trying to solve.
Yes, exactly. Yes.
So
It's exactly something. Is that you replace n with n over 2. When you replace n with n over 2, this guy gets Tn over 2, Tn over 4, Cn over 2, and you keep writing that. Eventually, you will reach to a geometry sum. And all of these details that for simplicity are working on the slide, and I can show you on the slide. On the slide, I try to post all details. Just a moment, let me show you a slide. See, this is what we have on the slide. On the slide, see, after reaching to this part, then we will use, okay, sorry, on the slide also we don't have this, sorry about that. Sorry. I'm sorry. So lazy, teacher, so lazy. This guy can be done by using a substitution or recursion. By substitution, you just replace n with n over 2, and here you will get Etn over 2, Etn over 4 plus Cn over 2. And you continue substitution, eventually you will reach to a geometric sum. And that geometric sum asymptotically is same as Cn. I can post a short video on Carmen and explain about this. I think that's better. I'll do it by today after. I will post a short video on Carmen and I will explain about the geometry sum here. Maybe that's helpful for some students.
Should we show our work in solving that last recurrence?
It depends, if it is given that, for example, you can assume that asymptotically this is same as Cn, you can ignore it. If it is not given, yes, please show your work. Yes. Any questions, any comments about this problem? It is a tricky problem. Then if you have the same problem in the exam, then hope sure it makes sense that for everyone, that's what we did for this problem.